Hello, today we are covering lesson 7.4, parallel lines and proportional parts. You guys will be able to use proportional parts within triangles and within parallel lines. We have one new vocab term, mid-segment of a triangle. And then we have our beginning to our lesson. So proportional parts within triangles. When a triangle contains a line that is parallel to one of its sides, the two triangles formed can be proved similar using the angle-angle similarity postulate. Since the triangles are similar, their sides are proportional. So if you look at this example, we saw one of these the other day. You have reflexive angle A to itself. If you extend our parallel lines and this transversal, we have these two angles that are congruent because of the corresponding angles theorem. So with that in mind, we have two similar triangles, the smaller one and the larger one by the angle-angle similarity. That's what it was saying above. So if a line is parallel to one side of a triangle and intersects the other two sides, then it divides the sides into segments of proportional lengths. So we have two parallel sides. They cut the other sides. We can then make a proportion based on that. So we have AB over BC equals AE over ED. So before we would have done the small triangle over the big side and then the other side over the whole side. We don't have to use the whole side when we have parallels. So let's try one. We have triangle RST. RT and VU are parallel. SV is 3, RV is 8, and UT is 12. We're finding SU. So instead of doing the whole thing, although we could set it up like that, we could do 3 over 11 equals x over x plus 12. Totally valid to do part over whole and part over whole. Although unnecessary now since we have parallels. So I am going to do 3 over 8 equals x over 12. Notice I still do this piece. If this piece is first and this piece is second, this piece is first and this piece is second. I still have to be particular about the order. I can just use the pieces instead of the large triangle. I go ahead and solve. 8x equals 36. Finish solving for x, and this equals 4.5. If you would like to see the old way, you'll notice you end up getting the same thing after you distribute. You also get 8x equals 36, which means x equals 4.5. Either way is a good way. Then we have triangle ABC. ACXY are parallel. We have the markings of the sides for us. I'm just going to go ahead and set this up to solve. I'm going to do 10.5 over 4 equals x over 6. Cross multiply, 4x equals 63. And I end up getting x equals 15.75. All right, now we have the converse of the triangle proportionality theorem. So we still have the triangle proportionality theorem, it's just the opposite now. So if a line intersects two sides of a triangle and separates the sides into proportional corresponding segments, then the line is parallel to the third side of the triangle. So it's saying if we are given proportionalities, then we know parallel. So we're going to check it. So in triangle DEF, DH is 18, HE is 36, DG is half of GF. Now this is a little different than what we usually see. We don't usually have an expression here. I'm going to challenge us to just come up with a side length for GF. I'm going to say 12. I just picked that out of thin air, just so I could then test what DG would be. So DG in this case would be 6 because it is half of GF. Now I can set up and check proportions. So I can say, well, if these are parallel, that means 36 over 18 should equal 12 over 6. This is a example, the 12 over 6. So we can either check by cross multiplying and get that 36 times 6 is 216, and that 18 times 12 is the same. That's one way to check. Or you can just reduce the fractions. We end up getting 2 over 1 and 2 over 1, so that checks out. Since these check out, they either both check out or they both don't. Since they both do, we know that, yes, GH is parallel to FE by the converse of the triangle proportionality theorem. We could also just say the proportions or ratios are equivalent. Alrighty? We'll try another one. We have WXZ is a triangle. XY is 15. YZ is 25. WA is 18 and AZ is 32. So we can check once again to see if these guys are parallel. That's our big question here. Are those parallel? WX and AY. We can set up fractions between the sides of this over this, which means I need to do 15 over 25. I'm going to check if my fractions reduce to the same thing. So I get 9 over 16, but on this side I get 3 over 5. Now notice as a decimal, they're sort of close to the same thing, but as a fraction, they're nowhere near the same thing. So we can say WX is not parallel. You can just put a slash through the parallels. Not parallel to segment AY because the sides are not proportional. Alrighty, now we have a mid-segment of a triangle. Is a segment with endpoints that are the midpoints of two sides of the triangle, meaning R and P and Q are midpoints. Every triangle has 3 of these mid-segments, so that's just where you connect the midpoints together. This triangle has RP, PQ, and QR as mid-segments. A special case of this triangle proportionality theorem is the triangle mid-segment theorem. A mid-segment of a triangle is parallel to one side of the triangle, and its length is 1/2 the length of that side. So, you know that we have a mid-segment here. That means these sides are split into congruent pieces. The cool thing about this is, in this case, and all cases like this, the triangle mid-segment theorem tells us that JK is half the size of FG. So let's use it. In the figure DE, and there's a typo here, this should say FE, are mid-segments of triangle ABC. So we know that because these are mid-segments, we have midpoints. We can mark some congruences. Not that that's necessarily helpful, but it is true. And we can mark some parallels. So we know that DE is parallel to BA and FE is parallel to BC. So if we are finding the distance of AB, we know that has to be double the size of his parallel buddy. Now that's only with a mid-segment. If you're not given a mid-segment, you don't know this. But double 5 is 10. If we need to find FE, we know that is half the size of his parallel buddy. So 18 divided by 2 is 9 for FE. And that's all of those, but they do also ask us to find an angle measure. So we have angle AFE that we're going to find. I'm going to extend my parallels. Let's extend my transversal, and I notice that this angle and the angle in question are alternate interior angles. So the measure of angle AFE is 87 degrees. All right, we have another one like this. In the figure, DE and DF are mid-segments. Mark everything that we know about them. And now we are trying to find BC. He's double the length of his parallel buddy. So 8 times 2 is 16. If we try to find DE, he has half the size of his parallel buddy, so 7.5. And if we try to find the angle measure, AFD, extend my parallels, extend my transversal. AFD is this angle right here. I notice that these are once again alternate interiors. Don't get too caught up with that. You might sometimes have consecutives or other types. It's not always just the degree on the picture. But in this case, once again, we have alternate interiors, so they are simply congruent, where measure of AFD is 122 degrees. All right, part 2. Really actually quite similar to part 1. We have proportional parts of parallel lines. So another special case of the triangle proportionality theorem involves 3 or more parallel lines cut by 2 transversals. Notice that if transversal A and B are extended, they form triangles with the parallel lines. That's why it's very similar to our previous examples. So proportional parts of parallel lines, if 3 or more parallel lines intersect 2 transversals, then they cut off transversals proportionally, and you can set up another proportion. So we have that guy, and then you have this one set up as your proportions. Okay? So let's do an example. In the figure, Larch, Maple, and Nuthatch Streets are all parallel. So I'm going to mark those out. The figure shows the distances between city blocks. So we know the distances between the parallels can make a proportion. So I'm going to do 26 over 13 equals x over 16. Now I could just go ahead and solve this proportion. I end up getting 13x equals 416. I divide, and I believe I should get 32. Yep, that is true. So x equals 32. Now, a possibly simpler way to do this is to go ahead and reduce this fraction. 26 divided by 13 is actually just 2 over 1. And then I cross multiply. That gives me one less step that I have to do later. Same answer though, so we're good to go. So the length between Larch and Maple on this specific road is 32. We have another one in the figure. Davis, Broad, and Main Streets are all parallel. The figure shows the distance in between city blocks. Find x. So once again, set up a proportion between our city blocks. 24/8 equals 15/x. I'm going to go ahead and reduce to begin with here. So 24/8 actually reduces to 3/1 equals 15/x. Go ahead and cross multiply. I end up getting 15 equals 3x. So x will equal 5. And I'm good to go. That will plug in here. And then we have one more corollary. We have congruent parts of parallel lines. If 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So notice how AB and BC are congruent between these parallels. That means that EF and FG must also be congruent. So let's use it. Find x and y. If I know these are congruent between parallels, I know that the other two must be congruent between their parallels, okay? So I can just go back to congruences. I don't even need to set up a proportion when we use this specific corollary. Now, it only works if we actually have congruences marked or told to us. We can't just assume that is happening. So x equals 6 here. We can go ahead and set up and solve for y. So y will equal 2. And I'm actually good to go. You can plug them back in to check to make sure you actually solve correctly, but those are the answers here. And lastly, we have this idea of the corollary again. We have congruences here, which means we also must have congruences over here since these are parallel. So I'm going to start by solving for A. Now B is a little trickier just because of the fraction, but really it's the same thing again. I'm going to go ahead and keep mine in fraction form. I'm just going to make a common denominator with this 3 over here, because 9/3 is the same as just 3 if you reduce. So I gave it a common denominator. Now I go ahead and subtract 5/3b across the equals. I get 4/3b equals 2. I multiply by the reciprocal to solve for b, and I get b equals 6/4. Now I should reduce that to 3/2, which is actually also equivalent to 1.5. So either the reduced fraction or the 1.5 are good answers. Okay, that is all I have for you today.